Recording in progress.
A vector in R2 is a vector that consists of an ordered pair of numbers. It's a vector, so we put a little arrow over the top of it to indicate that it's not just an ordered pair like the coordinates of a point, but, well, a vector, okay, that can be represented by an arrow. For example, the vector 6, 3 could be represented by an arrow from the origin to the point 6, 3 in the coordinate plane. Similarly, vector 2, 4 could be represented by an arrow from the origin to the point 2, 4 in the coordinate plane. So here we have two vectors, and I called this one V, and I've called this one W. So I could say, okay, V equals 6, 3. Arrow over the top of it to distinguish it from the point 6, 3. W equals the vector 2, 4. Similar explanation. Arrows over the name of the vector and the ordered pair. A vector in Rn for linear algebra is generally going to be considered to be a vector with its initial point at the origin and its terminal point at, well, in this case, 6, 3, in this case, 2, 4. Okay, at the coordinate point corresponding to the ordered pair. If I want to add two vectors, well, the sensible thing to do in adding these, and this is exactly what we do, is V plus W, of course, is 6, 3 added to 2, 4. Now you can't add two coordinate points, but you can add two vectors. And there's a very simple graphical representation of how you do that. Well, this just says you do 6 plus 2 and 3 plus 4, the most obvious thing that you could do. Now, in the picture, that corresponds to a vector that's diagonal on a parallelogram defined by V and W. Now, the parallelogram defined by V and W, well, it's very simple. And what in the world happened to my yellow chalk? Well, we won't bother color coding, but the vector W is going to look like this. Okay, put head to tail with V, you could have the vector W here. Now, put head to tail with W, the vector V could go here. And this would form a parallelogram because W can be thought of as a displacement vector. We don't think of displacement vectors in linear algebra. We do in many other, in physics and engineering. But V is a displacement that moves you 6 units in the horizontal direction and 3 units in the vertical direction. So if from this point, which is a point 2, 4, you move 6 units this way and 3 units this way, well, where do you end up with? Where do you end up? Well, it's going to be at this point. And you're going to have coordinates 8 and 7. We'll see that in a second. Okay. So again, doing this addition, we get this. And that's going to agree with what we get there, because if you move from the point 2, 4, if you move 6 units this way and 4 units this way, which would correspond to this side being equivalent to this vector, now you're going to be up 4 units, and then you're going to move over 6, but more importantly, up 3 units. So you're up 4 units, and you go up 3 more, and you end up 7 units up, 3 plus 4. Similarly, if you are at 2, 4 and move over 6 units, well, your x-coordinate is going to go from 2 to 8, which is exactly what you get here. Now, the picture of this is simply that the vector V plus W starts at the origin and moves to the opposite corner of this parallelogram. So this is the vector V plus W. Again, in adding vectors in other fields, and we just mentioned this, we put the vector W head to tail with the vector V. And that gets us to the vector V plus W. Okay, so that's pretty easy to understand. In other fields, you got to worry about angles and arctangents and sines and cosines and stuff. And in this course, for the most part, we don't deal too much with that. So it's actually kind of simple here. Okay. Well, another thing we might do, what if we wanted to do two times the vector V? Well, we would do 2 times then the vector 6, 3. And that would give us, well, 2 times 6. 2 times 3, which is, of course, 12, 6, would give us the vector 12, 6. So that means, we'd go over 12 units from here, maybe to about here. And up 3 and 3, which would be 6 units, that'd be about here. Or like here. Okay, so the vector 2V would go from here to here. Actually, I have better first try. Although my 6 here kind of looks like my 7 here, that figure isn't exactly correct. If you draw the figure carefully, everything works out. Okay, so here's the vector 2V. Now it might be a little hard to see my original vector V because I kind of put the 2V on top of it. But let's just make sure we got a white vector here and part of the green vector here. Now you might represent the vector 2V from here all the way out to here. Just take this vector and put it here. And your book kind of does that in some cases, at least in the homework, but you'll sort that out. Okay, so this is pretty much how you add vectors and multiply vectors by constant numbers. So there are definitions, and you can read those, but they're pretty obvious. It's pretty obvious if I add V plus W, I'm going to get the same thing as if I add W plus V. So there's a commutative law. Scalar multiplication, there's a distributive law. Okay. Which just says that C times V plus W equals 3 times V plus C times W. Now you might want to write that out. For example, well, I'm not going to take the time to write it out here. Pretty obvious that if I did 2 times this sum, well, of course, it would give me 16, 14. Okay. Now, if I do 2 times this vector plus 2 times this vector, it's going to give me the same thing. 2 times this vector is 12, 6. 2 times this vector would be 4, 8. 12 and 4 gives me the 16 I mentioned before. So you can write that out. It's very simple. Look at the examples. And other properties, what it comes down to then is that vector addition has the same properties as just plain old addition. Okay. Now, one important property is the identity. Addition. is zero vector. Okay. And we can call that, so we'll write that as a zero with an arrow over it, meaning the zero vector. What's an identity? Well, it says that V plus 0 equals 0 plus V equals V. Well, if you add a pair of zeros to whatever your coordinates of V are, or W or anything else, it's not going to change those coordinates. So this is very easy to see. Then we have inverses. For every V, negative V is the additive inverse, meaning really negative 1 times V. And the defining property of an inverse is that if you put a vector, in this case, a vector with its inverse on addition, you're going to get the identity. And the general idea of an inverse is you combine something with its inverse, you get the identity for whatever the operation is that you're using to combine them. Some operations allow inverses on some fields or rings or whatever, and some don't. Well, you have these abstract properties, and it's important because once you have these properties, you can solve vector equations. And so if we have, let's say, an equation now like two V minus 3W equals U. Now these are vectors. Okay, then we can solve for W. Okay, well, we can do 2V minus 3W minus 2V equals U minus 2V. We can have the same quantity, negative 2V, to both sides. And since we have the inverse property, 2V and negative 2V add up to the zero vector, which then added to 3W just gives us 3W. And now we can divide by the negative 3. So that negative 3W over negative 3 equals U minus 2V over negative 3. Since scalar multiplication distributes over addition, this is an addition of U and negative 2V, and this is a scalar multiplication of this thing by negative 1/3. So negative 1/3 times U minus 2V is negative 1/3 of U minus 1 minus negative 1/3 of 2V. And the result is that you can treat these just like algebraic quantities. So if you know what U and V are, you can solve for W very easily. Okay. I'll observe that if these are vectors in R2, vectors with 2 components, this would give you 2 simultaneous equations for W. Okay, the first component of W has to equal negative 1/3 the first component of U and 2/3 first component of V. And the second component, you get the same equation for the second component, but the second components are going to be different. And that's going to give you different results for W. Okay. vectors in R3, well, you got three components, and you could represent these things in three-dimensional space. So let's say you have the vector 2. Let me draw a vector. And okay, so let's say I've got a vector here. Now you don't know how far forward or backward this vector is. To get that, I'm going to project it down here and over here and over here. And then I can also project back to this third axis, okay, parallel to a segment from here to here. And I get this component. Now, what numbers might make sense of this? Let's say this is 2. And this over here is, let's say, -3. And up here, this is 4. So now I've got the vector 2, -3, 4. Represented in three-dimensional space. I wish I had room to draw that bigger, but I don't. And this looks like some kind of a strange symbol, but that means this is 4. Okay, so here's 2 on the x-axis, let's say, or let's call this the x1 axis. Call this the x2 axis, and this thing up here is the x3 axis. I could use X, Y, Z, but if I go into a bunch of dimensions, I'm going to want subscripts, just like we've done with simultaneous equations. Okay, I could do all the same things in R3 that I did in R2. It's just a little harder to draw and a little harder to visualize because your planes change and all kinds of things change. If I want to do 2, -3, 4, plus -5, 2, 7. I'm not going to attempt to draw it here. I could, but that equals 2 minus 5, -3 plus 2, and 4 plus 7. We just add the numbers component-wise, we say. -3, -1, 11. Okay, that could be illustrated over here. -5, 2, 7. We'd have to go -5 in this direction, which will take us off the board. And then 2 in the x1 direction. Sorry, -5 in the x1 direction, -5 in that direction, which we can do. That'll put us over here at -3. And then we'd go 2 in the x2 direction. Well, that would bring us over to here. So we'd be at a point like here down in the x1, x2 plane. And then we'd have to go up 11 units. That would put us at about here, and our vector would look something like this. And we could draw, this vector and this vector with a parallelogram. Parallelogram would be in some plane, which is a plane within three-dimensional space, and we'd get a reasonable picture. Now, your book might or might not show you pictures, I don't remember. But there we have the idea of adding vectors in R3. Vectors in R4. Typically, we have an x1, an x2, an x3, and an x4. And you don't even try to draw them because you can't draw in 4 dimensions because we live in 3 dimensions. We have no concept of what a 4th dimension would look like visually. Now, there are things we can do. We can project 4 dimensions into 3 and get some feeling for what this shape might at least look like if we project it from different angles, but we still don't have a very good feeling for what the 4-dimensional shape really looks like. We can learn things about it, but we can't still really visualize it. We just visualize aspects of it. Okay, and we don't worry too much about the geometry of it, although that becomes important in many fields. We think in higher dimensional spaces because, of course, there's no limit. We could have a 26-dimensional space with an x1 through an x26. And lots of luck visualizing that. we can still analyze it. We can still do everything in that space that we can do in R2 or R3. We just have more components. We might end up with 26 simultaneous equations instead of 2. And of course, we use machinery to solve those equations, but we understand the idea. So all this stuff extends into higher dimensions. Vectors in Rn, where n can be any number. There. Okay. You got x1, x2, dot, 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 up to xn, and I throw xn minus 1 in there, just to indicate that we're just, it could be a million dimensional space. And don't think that people don't deal with million dimensional spaces. In data analysis, a million dimensional space, not even a particularly big one. Still, the techniques that we use can be understood in terms of R2 and R3, 2-dimensional and 3-dimensional models. Okay, well, that's the idea of vectors in Rn. Your homework, you do a lot of pictures of vectors in R2 and a lot of multiple choice, but they're pretty good multiple choice questions. You're not going to choose the right answer unless you pretty well understand what you're doing. And then there are a few questions toward the end of the chapter that get a little more interesting. Okay, so like solving vector equations. Well, we just solved one. That's how you solve a vector equation. You can just use scalar multiplication and addition, just like you would with real numbers. I won't say that. Oh yeah, what I do want to say though is, one thing is, unlike with numbers, you can't divide or multiply by a vector, okay? Okay, there are products of two vectors. There's what you call the inner product, and the cross product is kind of an outer product. So you could have inner product. I'll say inner and cross products. They don't act like multiplications. Real numbers. So you can't divide by vector v. Okay. So forget in solving equations about things like trying to divide by the vector or multiply by the vector. It's not going to help. Okay. That gets you through right there a whole lot of section 4.1. But we do want to talk about a couple of more complicated things like linear combinations and so forth. And I was going to pause to make sure I'm not leaving something up. I'm going to just use my better judgment, just go directly to linear combinations. Okay, make sure I can see this into the board. Okay. Let's let v equal 2, 3, and I'm just going to do it in 2 dimensions. In higher dimensions, just add numbers to your list. If u is 2, 3, v is, and v is, let's say, -3, 1. And the linear combination of u and v is, I like to say what it is, and then I'll say it in symbols. A sum of multiples of u and v. Now, the only kind of multiples we know about on vectors are scalar multiples. So I didn't put the word scalar there. I just said a sum of multiples of u and v, and that really gets it. We'll just go ahead and throw that word scalar in here to be a little more rigorous about it. But we're just trying to get the feel, a sum of multiples. Well, what could that mean? Well, that could mean the sum of 2 times u and 8 times v. Or negative 7u plus 5v. In general, a linear combination of u and v is a sum C1u plus C2v. Now that is a sum of multiples, right? And C1 and C2 could be positive, negative, UV could be any vectors. Okay, and this isn't confined just to R2. If I've got 2 vectors, these vectors could be in R3. I could do a sum of multiples of 2 vectors in R3, or R4, or R17, or R2,000,005. Okay, I can always do a linear combination of 2 vectors. Now, one of the big questions is, and this gets back to simultaneous equations and kind of illustrates the point that everything in linear algebra comes back to simultaneous equations. Maybe that's an overstatement, but not much of one. Okay, so here's a question. W equal -5 be expressed as a linear combination of u and v. Now, this is a big question. Very, very important question in linear algebra. Maybe the biggest question you've seen so far. So it's not hard to interpret what this means, but maybe you need a little help. So let me do that for you. Okay, so well, the linear combination of u and v is C1u plus C2v. We don't have to use C1 and C2, but that's what you're going to see in your book. And that's what's used in most textbooks. You could call this Q1u and Q2v if you want to. You could call it Omicron 1u and Omicron 2v if you knew how to write an Omicron, but we probably ought not to talk about Omicron right now, right? Kind of in the peak, or hopefully just a little past the peak of this Omicron wave. Okay, so, and it's Omicron. Don't go into mathematical circles and call it Omicron. Maybe the medical field wants to call it Omicron, but it's Omicron. Okay. I think that's the way it's pronounced in Greek. And that's certainly the way all mathematicians pronounce it, as far as I've heard. Okay. A typical linear combination of u and v is C1u plus C2v. Nothing sacred about C, but that's what's usually used. So the question is, can we solve the equation C1U plus C2V for C1 and C2. If we can solve it for C1 and C2, then we will have our linear combination. Well, we write out this equation. There we have it. Well, that gives us C1 times vector, what was U23, plus C2 times the vector negative 3, 1 equals W, which is 5, negative 4. That's our equation. Well, what's C1 times 2, 3? It's 2C1, 3C1, plus negative 3C2, C2 equals 5, negative 4. By a rule for scalar multiplication, which is an obvious rule, but an obvious geometrical interpretation that you need to understand, so make sure you think about that. Okay, so we have this. Well, let's see. Now, if we have these vectors, of course, we can add vectors component-wise. We get 2C1 minus 3C2. And the second component gives us 3C1 plus C2. And that should equal 5, negative 4. Okay, none of that's difficult. So, well, how do we solve this? These are vectors. I didn't say it before, but the only way two vectors are equal is if the first component of this one equals the first component of this one, and the second component of this one equals the second component of this one. In other words, component-wise, they have to be equal. They have to be equal on every component. So we have C1 minus 3C2 equals 5. And 3C1 plus C2 equals negative 4. So our question of can we express this as a linear combination of these becomes a system of two simultaneous equations. How do we solve this system? Well, my preferred method is to write the system as a matrix equation. That can also be written as an augmented matrix and reduced. Okay. You could solve it by substitution, but we don't do much of that in linear algebra, except back substitution and stuff. We don't solve a system by substitution. In other words, we could solve this for C1, we get what, 5 plus 3C2 all divided by 2, and plug that in for C1 here, give us an equation for C2, and so forth. A standard method that we learn in algebra and is mainly valuable not for linear equations, but for nonlinear equations when you can't do elimination the way we do for linear equations. And of course, you can solve the system by elimination. Okay, so there are lots of ways you can do it. We're going to solve it by matrix method so that C1, C2 equals the inverse of the matrix 2, negative 3, 3, 1 times 5, negative 4. Well, the inverse of this matrix is just the matrix you get if you switch the numbers in the main diagonal and change the signs of the numbers in the second diagonal. So I'm going to give myself room. Sometimes I just write things down without thinking about what I'm doing, which usually means I write something down that I saw. Okay. Inverse matrix is going to have a 1 here and a 2 here. There's going to be something else because you got to divide by the determinant. And I can use that terminology since we've already seen the determinant. They haven't got the determinant in there yet, but we know that we're going to divide by A11, A22 minus A22, A12, A21, okay? And that's going to be what? It's going to be 2 minus negative 9, which is plus 9, which is 11. So it's 1 over 11, 3 over 11. And the details of this should be pretty obvious to you. Okay, now let me just double check, make sure I did the determinant correctly. It's 2 minus negative 9, which is 2 plus 9, which is 11. So I'm dividing correctly, okay? Now, if I've done everything right, and you know that that's not always the case, this gives us the vector 5 11ths, negative 12 11ths, which is negative 7 over 11, and negative 15 11ths, and negative 8 11ths, which is negative 22 11ths, which is negative 7 over 11. Bad looking slash there. Negative 2. Well, if we come back here, I mean, this tells us, of course, that C1 equals negative 7 11ths, and C2 is negative 2. And yeah, I think I'm able to see the whole board there. Okay, I wanted to make sure. Well, I'm out of board space, but I want to do this in the board. So I'm going to borrow some of the space down here. Okay, so I'm saying that W equals C1 V1 or C2 V. Let's get my variables straight. Okay. So I'm saying that W should equal C1U, which is C1 times 2/3. C1 equals this, not that. C1, C2 equals all this, which equals this, meaning C1 equals negative 7 11ths, C2 is negative 2. And I'm not clear that that's actually going to work out, but let's see. There's a very good chance I made a mistake there, but you can correct it. W equals C1U plus C2V equals well, you know, I kind of know that's not right. So I'm going to pause the video and see just where I lost my mind on this, because it should be pretty straightforward. But I obviously did something wrong, and I'll correct that off camera. Okay, just to show you the correction. I said it, but I didn't do it. I got to change the sign of these two. So as I said, sometimes I copy what I see rather than what's there. Okay, so these have to change sign, and that's going to change my numbers down here. So let's correct that. So I have 5 11ths and 12 11ths, which is 13 11ths. And down here, I get 15 11ths and minus 8 11ths, which is 7 11ths. Make sure 15 minus 8 and 5 and 12. 5 and 12. I did 1 and 12. I saw the 1. 5 and 12 should be 17. I've got to stop seeing things out of my peripheral vision that tend to invade my writing. Okay. So let's go ahead and change this expression, and then we'll see if it actually works. And I'm not totally convinced it will, because I tend to be a little careless. I prefer, though, to do this, to really be doing this rather than copying it down from a piece of paper I have to keep looking at. It loses all kinds of spontaneity. But then, of course, there are mistakes. Okay, so figure out how I should balance it, but this is the way I choose to balance it. Okay, now that's going to work. It didn't work before because I had a whole number here, and I had a fraction with denominator 11 here. It was very clear that I was going to get a fraction with denominator 11, which is not going to give me 5 and -4. Okay, whether you understand that or not. Okay, so that equals what? 17/11, so I'll get it in detail, times 2, 3, if I have room, plus 7/11 times -3, 1. And that's not going to work either. That's not going to give me 5. Okay. I mean, this should equal W, which means that my first component should be 5. So still I've got I've got a mistake because I didn't change these two. I don't know what I did. Okay, this is wrong. Okay, this is going to give me 5 and -12. Which is -7/11. Get this right yet. -15 and -8 is -23. Now let me just see if that's likely to work out. -7 times 2 is -14, and -7, -23 times -3 is -69, and -69, 14 is -55, and -55 divided by 11 is 5. Okay, I think maybe I've got it. The question was, a good idea to do this line. Okay, this -7/11. And this is -23/11. -7/11, -23/11. Okay. Now this is going to give me -14/11. -7/11 times 2 is -14/11. And -21/11. Very similar calculation. Plus -69/11. Plus (1/11). That works out except it doesn't. I'm sorry. -23/11. Okay, that works. That's going to get it to so easy. Parenthesis, not a bracket. So it equals this. And now if we add these up, we get plus 69, not -69. We get -55. We get plus 55/11. And 44, yeah. Yeah, -44/11, which equals 5 -4. And now, forgetting about all the details that I messed up, we see that the process works because we've expressed W as a linear combination of U and V with constants. C1 equals -7/11. and C2 equal negative 23/11. And we see that answering this question leads us immediately to an equation equivalent to two simultaneous equations and two unknowns, C1 and C2. They can be solved and reduce an augmented matrix using an inverse matrix, okay? Those would be the two most likely ways to solve the equation. I mean, of course, reducing the augmented matrix is equivalent to another possibility, which is just doing elimination from the original system. This is more efficient than either of those if you get the inverse easily. Okay. And usually you can get the inverse more easily than you can complete the row reduction, but it's kind of equivalent. Now, you should understand why that is, because to get the inverse, you take the matrix, augment it with the identity, reduce this to the identity, and you get the inverse. It's a little more work than maybe doing the row reduction to upper triangular form and using back substitution. You have all those methods. Okay. If W was a vector in 3 dimensions, it would have 3 components. And then you would get, if you're just trying to do it as a linear combination of 2 vectors, also 2 vectors with 3 components, what would happen? You would have 2 equations. Well, you have this equation, which would lead you to 2 simultaneous equations, but you'd have a 3rd component here, okay? So you'd have 2 simultaneous, I'm sorry, you'd have 3 simultaneous equations. You'd have 1 simultaneous equation for the 1st component, 1 for the 2nd component, like we have here. Well, here, 1st component equals this, 2nd component equals this, but then your 3rd component would have to equal a 3rd number. So we'd have 3 equations and 2 unknowns. And unless you're very lucky, or unless there's something going on, you're not likely to get a solution. You have too many equations for the 2 unknowns. The solution to the first 2 equations would not necessarily be a solution to the 3rd equation. Well, there are geometric interpretations of all that, but we're not going to get into that right now. The main thing is, the most important thing you can get out of this, other than the picture of the vectors and an understanding of the algebraic properties, which is all pretty easy, is how you express a vector as a linear combination of a set of other vectors. And that comes right at the end of your problem set. Okay, well, that should give you sufficient preparation. So hopefully we didn't run on too long with this, and I do apologize, but not really, for my mental errors. Clerical error led to mental error, led to another clerical error and another mental error. No real apology for that, because I like the way that this works more spontaneously. So good luck with your homework. And I will see you after our one-day absence.